Well, hello everybody. So, in this particular class, I would just touch upon certain things that I could not complete in the last class, particularly in the more complex form, the configurations which should be including the multiple feeds, tight stream draw and external refluxing arrangement. So, particularly we will be discussing about the arrangement for side stream draw and what is this external refluxing arrangement, why do you need it. But before that, there were certain things about the feed which I would like to mention, and I will touch upon those things and then I will proceed. And after that, definitely we go for the design of the distillation column. So, in the feed zone, again just like I had mentioned during the reflux entry into the column, that you just cannot pour the reflux into the column through the nozzle. The same thing for the feed zone. Normally, what do we have? We have a tangential feed entry in the large columns. Now, when you have just a liquid feed, it can be introduced in the downcomer, which leads to the feed tray. So, therefore, there is a downcomer from the top tray on the feed tray. So, in the downcomer you can introduce it. Now, tell me, if you have a liquid vapor feed or you have a feed of a liquid feed at its saturation point, under that condition if you are introducing it at the downcomer, what do you expect is going to happen? The liquid feed, it is going to flash, and if it is a vapor liquid feed, vapor is already available in this particular case. So, what this vapor would try to do? It will try to rise up through the liquid here, and while it tries to rise up, it will definitely try to take some amount of liquid with it. This is going to lead to entrainment of the liquid from here, and this leads to something which is known as a downcomer entrainment or a downcomer flooding, which we will be discussing in more details when we go for the design part. So, naturally for the liquid vapor feed, what do we have is for an efficient removal of the liquid and the vapor, such that the liquid it can flow down and the vapor it can flow up. So, the liquid vapor feed, when it is introduced through the nozzle, it strikes on a baffle plate. This is known as a splash baffle. It strikes on a splash baffle, and then the vapor goes up and the liquid it comes down in this particular in this particular case. And just to mention, although we are not discussing packed columns, so therefore, just I would be mentioning that for the packed columns, as I had mentioned earlier, that there are two packing sections. So, between these two packing sections, usually the feed is introduced, and then there are of course arrangements for distributing the vapor and liquid across the column section. We will be discussing it later. Well, very frequently that we not only need the distillate or the bottoms, but we also need a side stream draw. Side stream draw is drawn from any plate. It has a composition between the distillate and the bottom, and depending upon the plate composition, it is drawn from any particular plate. Now, tell me one thing, how do you draw it out? Is it that you just have a nozzle here, you open the nozzle and simply draw out the side stream? You cannot do it, the liquid vapor will be coming and the equilibrium inside the column is going to be disturbed. So, the tray from which the side stream is drawn, it has got a slightly different arrangement from the other fractionating trays. In the fractionating trays, we will be going into the details. What do we have? We can either have some riser sort of things through which the liquid can rise, and then over the riser we can have such bubble caps through which the vapor can bubble through, or normally what do we have? We have several perforations. Through these perforations the vapor can rise and the liquid it flows across this column, across the tray, right. Well, for drawing out the side stream, we have a special arrangement, and this tray is known as a chimney tray. In the chimney tray, what happens? We have very long risers, such that the riser it ends above the liquid column in the tray, and the vapor which is rising through this does not come into contact with the liquid here. The vapor it rises, it goes out through the between the hat and the chimney, and then it rises up, and then it bubbles through the liquid on the upper tray, and in the upper tray the enrichment goes on as usual. In this tray, what happens? The liquid from the upper part of the column it enters, it flows through the tray, it collects in a draw off pan. In the draw off pan, we have got a draw off nozzle from where the side stream is withdrawn from here, and the remaining amount of the liquid, this overflows over a weir and it comes down into the tray below. It provides the internal reflux to the lower tray, and in this way your distillation or the enrichment occurs below the chimney tray, it occurs above the chimney tray. At the chimney tray, definitely this is not a fractionating tray, there is no fractionation occurring here, we just draw the side stream from this particular tray. So, therefore, this is ineffective as a fractionating tray. Now, it is quite natural. So, therefore, the internal reflux which goes to the tray from the chimney tray, it is less as compared to the liquid which flows from tray to tray. So, quite frequently we find that if you have to increase the internal reflux flow from the trays, or rather from the draw of trays to the trays below, and to reduce the vapor flow above the tray on which it is returned, we use something known as the circulating reflux streams. It also removes heat from the column. This is very common in crude distillation columns. Now, in this case, what do we do? Just below two side stream draws, or maybe below the overhead product draw and the side stream draw, we have an arrangement which is known as a circulating reflux, which means that from some particular tray we draw the liquid, we cool it and we introduce it, usually two trays above the tray. That means, if this is nth tray, then this is going to be the n minus 2 tray. So, therefore, it is usually drawn from here and the stream is cooled and it is returned 2 trays above the draw off tray. If we draw the circulating reflux from the third tray, we introduce it in the first tray. This is the way. So, quite naturally, in this particular way, what happens? We can increase the internal reflux and therefore, we can maintain the enrichment which we want in the trays below the draw off trays, and we can also reduce vapor flow above the trays. But it is quite evident that definitely this set of 3 trays, these trays, they are ineffective as fractionating trays. Definitely fractionation does not occur in the same extent. So, therefore, what we do is, by convention, the set of these 3 trays, they are taken as a single stage of contacting, and accordingly we compute the number of trays here. So, therefore, n minus 1, n minus 2, these 3 trays are taken as one tray, and accordingly the total number of trays are arranged here. And well, needless to say that the arrangement for drawing out the circulating reflux, it is same as the side stream draw. In the same way, we draw it from a chimney tray, and the arrangement for introducing the reflux, it is same to a feed tray arrangement. So, therefore, this was the basic the description of a conventional, the simplest distillation column, and then I discussed certain additional features which are there, particularly because you need side stream draws, and so therefore, it is very common. After this, we will be discussing the design aspects, the how to start a design, what are the inputs, out the deliverables, etc. Then we will be proceeding into the details of design.
Well, this is in continuation of what has been taught to you by Professor Das. That is basically about the fractionation and the fractionated parameters. The basics are already over, you are aware of the equilibrium and you are aware of the fractionated stages. And in this particular session, what I am going to deal with is basically the basics of fractionated design, the basic principles in fact. The detailed things would follow immediately after this. If you are talking about the design of a fractionator, the first thing that you need to know is about its configuration. That means, what exactly is a fractionator consisting of, and the next thing that is expected to be covered is, if you are going to design such a thing, what exactly will be the relationship between the different process parameters of the fractionator and how they are related to the functional output of the fractionator, that means enrichment from a feed composition to the product composition. The product could be the top product or the bottom product. Beyond this, we need to have a list of output for the design process. Quite naturally, we would like to fractionator is a steady state process. That means, we have to keep all the process parameters steady at their fixed values, rather at their desired values, and we must have some sort of handle with us, so that we can manipulate some of these parameters, or rather adjust some of these parameters, so that we achieve the functional objective, maybe a range of xp, a range of xt, or something similar. So, we need to know about the control of the process also. That means, we definitely will have to look at the parameters which are to be varied by the design group, followed by keeping provision for the operating group to change those using controllers, and also providing certain parameters which are important otherwise also, but need not have a direct control, but should be monitored, that also should have the monitoring facility. Beyond this, we have to find out a set of procedure for finding out the number of stages and the related operating conditions, which will be taken up after this. To start with, we look at the fractionating column, we go for a little bit of recapitulation. So, we know here that naturally, if my feed is XF composition, it will be split into a distillate with having a composition of XD and a bottom of composition XB mole fractions. In fact, we are going to use the same mole fraction as has been introduced to you. We also know the upper section is going to be the rectification section, the bottom section is going to be your stripping section. For any specific system, the extent of separation is going from XF to XD. If my top product or the distillate is my desired product, or going to an XF to XP if my bottom product is a desired product here. Now, we know about the functional requirements. We need to know really the number of stages in rectification, which is the enriching section number of stages, and the number of ideal stages in the stripping section. So, these are two parameters NR and NS, which definitely have to be provided by the column itself. So, a major step is to find out NR and NS, that is the number of ideal stages above the feed and below the feed, which will be dealt by the next detailing later on. Now, if you look at a distillation column, there are few operating conditions which decide these XD and XP. Basically, these are the operating conditions which are expected to decide the XD and the XB. The first thing is the column pressure. The second thing is top temperature. You already know that whenever we say column pressure loosely, we really mean the column top pressure, that is the convention. Similarly, the bottom temperature and the bottom pressure are also two very important parameters. So, if I write here symbolically, I will write here these as P top, T top, T bottom and perhaps P bottom. So, these are the four extremely important parameters which are to be held and manipulated and kept constant in order to achieve XD and XP, starting from a feed composition of XF. So, the next question comes up, how do these four operating conditions influence XD and XP for a given XF? Now, let us look at the distillation column itself. We look at the top portion. We have here a condenser. From below that, we have the accumulator. In our accumulator, we have vapor and liquid both. We have a reflux which goes back to the column, and here we have the distillate with a composition XD. The reflux flow is L. The reflux ratio is L upon D. This is about tray number 1. You definitely will be having here a pressure P top, rather you have a pressure indicated here, and the P top is basically this particular point. This is P top, and naturally you have the T top at this particular point also. The vapor, if I look at the top tray number 1, the vapor leaving from here as overhead vapor goes here and gets condensed. That means, on the liquid, from the liquid top, what leaves and whatever liquid you have here, they are in equilibrium. So, it is obvious that the top vapor which leaves and gets finally condensed, I am right now showing here a configuration which has got a total condenser with a composition of XD, the same composition XD remains here. So, XD is also the vapor composition. Now, this XD is what? This XD has been just generated from the top tray liquid. So, if we condense it, if we reduce its temperature by a small amount, the heavier components in larger proportion would start condensing. That means, the vapor would start condensing and a composition would shift from XD. So, quite naturally, this vapor is at its, this vapor is at its dew point. Now, whenever we say the dew point temperature, there is a corresponding dew point pressure. The dew point temperature here is what? The temperature of the top, which is T top, and the dew point pressure here is what? It is a P top. So, quite naturally, this XD is a composition, its dew point is T dew, its dew pressure is P dew, and what we know here is that this T dew is what? It is T top and this is P top. I am intentionally repeating this so that this becomes amply clear that by if I can alter these two conditions, my XD would change. That means, one thing is very sure, if I can somehow change the column top temperature, the dew point is going to change, because if I keep my pressure, sorry, this is actually my P top. So, if I change my column top temperature, my dew point would change for the corresponding pressure and my composition XD would change. So, this establishes that XD basically is a function of T top as well as P top. I believe this is amply clear to you. Now, I would like to add something more about the bottom section now. If you look at the bottom section, which has got a liquid, part of the liquid is vaporized and put back, and this happens in a reboiler, and this is basically my column bottom material with a composition what? The composition is XB, and what is here I have TB or my T bottom, and at what pressure? At a pressure of P bottom, sorry, at a pressure of P bottom. Here if I see, this is again a saturated liquid, it is giving off vapor. So, what happens here? So, this is at a condition of its bubble point. So, naturally your T bottom is equal to the bubble point temperature of B at P bottom pressure, and what? Its composition is XB. Therefore, I can also write again the way I had written in this particular case. My XP will be some function, if I call this F1, I am going to call this F2, of T bottom and P bottom. So, I believe you have right now an idea that if you would like to change the top composition x d and the bottom composition x b, one of the way is to change T bottom and T top. Now, there is something in addition to this. We normally would like to keep the column top pressure constant. If you calculate, it's something very interesting. Suppose we are talking about a 1.5 meter diameter column, and the column pressure fluctuates by an amount of approximately 0.1 kg per cm square. You will evaluate the pressure differential that it generates across the top tray. It will be in hundreds of kilograms force. That means, usually such pressure surges are sufficient to dislodge trays. So, one thing is true, normally you would not like the column pressure to vary, and so naturally you would like this to be kept fixed by using some sort of controller. So, you usually keep this fixed, and if you keep the column, this is the column top which is kept fixed. It is a column top which is kept, column top pressure which is kept fixed. We fix P top, we control T top, and the result is basically a fixed x d to the desired value. Now, once you fix P top, you will find your column bottom pressure will also get fixed. The reason is simple. The column top pressure has to be lower than the column bottom pressure, because the vapor generated by the deboiler, ultimately it has to pass through the trays. Across each tray there will be a pressure drop, and these trays typically will have roughly around 50 millimeter of liquid on it. Including other additional pressure drops, the pressure drop per tray normally amounts to roughly 50 millimeter water column per tray. So, since once we have designed and we have fixed, or rather while we are designing, if we have an estimate of the total number of trays involved in my column, I can estimate the column bottom by adding the total pressure drop in each. Now, in order to do this, to have a steady operation, we must have some parameters which are controlled. We need to have certain parameters which are measured also, and we definitely have to represent the control scheme using a P&ID. Before going into the control scheme, what we do is we talk about the design output list. Naturally, regarding the column, we have a lot of process parameters. These are the composition, the temperature and pressure profile in the column that we already have decided, the flow rates across each tray and their phases of feed, reflux, distillate and bottom product, the vapor boil up rate and the non-condensable vapor steam rates. Similarly, we have not detailed how to find these out, but whenever we are talking about the process output for the trays, we need to know the number of theoretical stages, the number of actual trays or stages or tower plates, whatever you may call, the feed tray location, the type of tray, tray diameter and layout, and naturally the operating percentage flooding and the pressure drop in each tray. If it is a packed section, there will be equivalent items. So, it will be number of transfer units or number of theoretical stages or per plate, and naturally the HTU or HETP, which are already defined in your mass transfer course. In case of packed column, the diameter has to be known, naturally that is the tower diameter. The depth gives us how many stages of equivalent contact we are providing, and the percentage flooding at the design conditions and the pressure drop. We definitely have to detail the packing material as well. Regarding the boiler and the condenser, we have to give the details. We definitely have to provide the pressure, the temperature and the heat duty, so that these can be designed by the appropriate group. In your reboiler and condenser, you are going to use hot and cold utility. Their requirement is also definitely a process parameter which has to come out from your exercise. When you are finally making a summary of the design, before that you have to give and generate all dimensional parameters which are listed here. These set of output is going to be the design basis, or rather the basis of drawing for making a fabrication drawing, which will be given to the fabricator for fabrication, and ultimately this will become your column itself. So, quite naturally these are all dimensional parameters which are listed here, which are height, diameter, location of trays, location of instrument nozzles and all. And definitely you have to have some idea about the safety aspects also. So, which will be detailed slightly after this, immediately after in fact. That means, as a part of the design of distillation system, you are going to provide a column with a complete specification for fabrication. That is the drawing that I have mentioned. The details of the heat exchanger, which are the condenser and the reboiler, pumps, piping and pipe fittings, their specifications and sizing, startup and shutdown facility and procedure, definitely this has also to be defined. You have to talk about and provide in the form of a P&ID the instrumentation control and the safety interlocks which are implemented through instrumentation, and definitely the safety valves or blow down arrangement and the flare for process safety, whatever is required for your plant, the distillation system has to be provided. So, these are basically nothing but the P&ID details of a fractionator, which I provide in the next slide. Here is the upper section. The upper section definitely shows streams, which is the reflux, which is controlled. The level is controlled by the distillate. This in fact has been told to you by while teaching in the other class. The pressure is controlled by the venting, and this is the basic arrangement what you have in the P&ID. But here I exactly cannot call it a P&ID because it does not include the piping details, it only shows the control scheme. Similarly, a question possibly will be coming up that how do you control your feed? Normally the feed rate is controlled and is an independent parameter for which your process is being designed, and it is nothing but a flow control valve in your feed line. So, this is basically the control scheme for your feed. If you look at the column bottom section, what you have is certainly the level control, which also has been talked about. You definitely have to control the column bottom temperature, because that decides the value of the XB here, and that is controlled by controlling the steam or the heating fluid input or the heat input to the reboiler. So, this is your reboiler, and the reboiler heat basically generates sufficient temperature, and your steam flow or the heating fluid flow is manipulated in order to control TB, which in turn fixes your XB. The level naturally decides the flow rate of the column bottom. Regarding the column pressure, I already have told you that the column pressure is decided primarily by a very interesting point, which is that the column, since it receives the liquid from the condenser, and the liquid in the condenser after the condenser is at a particular temperature which is decided by the coolant in the condenser. A typical example for which is, if it is cooling water, typically in Indian condition it will be entering at 35 and it will be leaving at 47, and we have an adequate pressure, adequate temperature driving force. That means, if my hot side is between the temperature of 52 to 57 degrees centigrade. So, if you are going to use a cooling water, possibly you will have a condenser exit temperature which will be anything between 52 and 57, which the designer has to decide. Now, that means inside your accumulator, that is going to be your temperature, and the accumulated pressure is the bubble point pressure of the distillate at the condenser exit, which is anything around say 55 degrees centigrade if your temperature of cooling water is 35 in and 47. So, that is something to note, that ultimately your accumulated pressure is decided by the coolant temperature. Now, the column pressure has to be higher than your this particular pressure. So, naturally the column pressure is going to be accumulated pressure plus the pressure drop in the piping in the overhead, which normally is highly oversized, and the pressure drop in your condenser. So, your column top pressure normally is found out by adding around 0.3 to 0.4 to the accumulated pressure, which has been found at a temperature of around 55 degrees centigrade using cooling water. Now, I have already said this, that the column feed tray or the bottom pressure will be the top pressure plus the tentative pressure drop in trays. We do not know that exact number of trays yet, but we can always make a guess. And assuming 50 millimeter of water column per tray, we can estimate the column bottom pressure as well. So far what we have decided is the design output and the basic steps and the principle based on which certain process parameters can be found out. So, the next thing should be finding out the details of the number of equilibrium stages which are required above the feed tray, that means in the enriching section, and below the feed tray, which is the stripping section. At the same time, we are also to note that the requirement of the number of trays depends on the reflux ratio. So, quite naturally, we need to have a procedure which is a McKeep-Thiele procedure, which relates the number of tray requirements for these two sections as well as the reflux ratio for a specific equilibrium system. Maybe benzene toluene, it could be alcohol water or any such equivalent thing. With this, I think I will stop here, and the next input shall be on the McKeep-Thiele method of estimating the number of stages and the reflux ratio relationship and what exactly it should be in your design case. Thank you.